Hi, my name is David Van Vranken, and I'm here to present to you Organic Chemistry 201, Organic Reaction Mechanisms 1 at the University of California at Irvine. And this is a course that's sponsored by the UCI Open Courseware Consortium. And let me start off by explaining to you the differences between Chemistry 201 and the second quarter in this two-course sequence, Organic Reaction Mechanisms Chem 202. In Chem 201, the primary concern of this class is arrow pushing. We evaluated our curriculum about 10 years ago and realized that the courses that we were offering were not giving one-quarter students a good introduction to how to push arrows in organic reaction mechanisms. And so we divided our course content into two different courses. So the first quarter, that's this course, which involves about 20 different topics covered over 24 lectures or so, covers arrow pushing and attendant concepts like energy, conformation, and structure. In Chemistry 202, which is not part of this course, we cover concepts like paracyclic reactions, the Diels-Alder reaction, Ene reactions, sigmatropic rearrangements, things like that. We also cover radical chemistry, conformation, and stereoelectronics, and mechanistic tools like kinetics and kinetic isotope effects and linear free energy relationships. So these concepts are not covered in this quarter, and this quarter will focus on arrow pushing. So let me go ahead and start off with a fundamental question in organic chemistry, and that is, what does it mean when you draw a mechanism? And so let me start off by presenting you with a simple mechanism, or a simple reaction, and let's ask some basic questions about that reaction. This is a hydration reaction of a carbonyl compound, something that's covered in most sophomore organic chemistry textbooks. And so what would you draw for a mechanism like this? I think you can see that in the product we formed bonds between this oxygen and that hydrogen, and a bond between this oxygen and that carbon atom. And so if you were to draw a mechanism, you know that this oxygen atom needs to be attached and you need to break the pi bond. And so why not draw something like that? And you know that you need to break an OH bond in the starting material, and so why not draw something like this? This mechanism is fundamentally incorrect. And if I go to the literature, or if I go to the World Wide Web, and I ask what's the mechanism for this kind of simple hydration reaction, I will get every single possible conceivable answer for that by looking around at what people say, even just the first step of this multi-step mechanism. So if I go onto the web and I ask what's the mechanism for this reaction, I'll find things like this as the starting point for this reaction. You might think that if this is really a stepwise mechanism, maybe I should use the oxygen lone pairs and attack this carbonyl carbon first. I can find other places that say that maybe the mechanism involves a small amount of hydroxide anion present in solution. And so I'll draw that mechanism like this. There's other mechanisms that suggest that maybe I should activate the carbonyl by using the lone pairs on oxygen to pull a proton off of the water as the first step for that mechanism. And I can find other reactions that suggest that maybe I ought to use a better acid to protonate that carbonyl. Maybe something like this small amount of hydronium ion would be present in the reaction mixture and could protonate some part of that carbonyl. So when I look all around, I find all different kinds of mechanisms for a very simple reaction. And so let's try to address that problem. Why is there so much diversity in an answer that ought to be very simple? What is the mechanism for a simple reaction? Let's start off with a simple question and answer session here. And I'll start off with simple question why. Why is it that if I ask any two organic chemists, so not students, but bona fide organic chemists, teachers, instructors, the people who grade your exams, a mechanism for a reaction, I never seem to get the same answer. And so the problem is there's just simply no agreement. It seems that nobody can agree on what the mechanism is. Why is it that when you look at the answer that you draw for a mechanism, when you're answering a question, and you look at the textbook, you find that what you drew is not equal to what's in the textbook? How frustrating is that? And there's no explanation as to why your mechanism is wrong and the textbook is correct. Why is it that if you go to a journal article, you write a mechanism for a reaction, and then you look at the published mechanism and your mechanism doesn't match? Does that mean your mechanism is wrong? What does that mean, that we never seem to find that kind of agreement? And there is a simple reason for all of these discrepancies. And the answer to this fundamental question of why there's so much diversity is that there is no definition for what an arrow-pushing mechanism is. Organic chemists have never sat down and agreed on what does it mean to draw an arrow-pushing mechanism. And so that's a question that we have to confront at the beginning of this course. If we are all going to agree that there's a difference between a correct mechanism or a plausible mechanism and an incorrect mechanism, or one that's implausible, we need to create a definition that works and that's consistent with what has been done in the past and what people should do in the future. And so let's start by that. Let's go ahead and give ourselves a definition for what an arrow-pushing reaction means. So the first and most important feature of an arrow-pushing mechanism, and you have to satisfy this, is that you need to break the reaction down into elementary reaction steps. A good mechanism is a series of elementary reactions. And that's critical. And I'll explain what that means. So let me redraw this hydration reaction so that we can discuss these aspects of an arrow-pushing mechanism in terms of these two components of the definition. So if I draw out this reaction, this hydration reaction, and I ask what's the mechanism for this, the key answer to this, the key to the answer, has to be a series of elementary reaction steps. The true mechanism for this reaction under typical conditions involves acid catalysis. So I need to start this mechanism by drawing an acid. And I'll abbreviate that with this depiction HA. Let me draw it a little closer here. And I'll use the lone pair here on oxygen to deprotonate that hydrogen, that proton that's attached to my acid, which I've symbolized with HA. And so when I draw the next intermediate, I now have that proton on this oxygen with 3 bonds to oxygen. I call that an oxonium ion. And so now that I've activated this carbonyl carbon, I can now use the lone pairs on my water nucleophile to attack that carbonyl. So I now have the first step. In the second step for this reaction, I've created this new bond to oxygen, and now all I need to do is to deprotonate my nucleophile in order to create the final product. And here I can use the counterion, the conjugate base from my acid, to release the proton. So this is a correctly drawn mechanism. So the important thing that I've done here is that I have broken this down into a series of elementary reaction steps. And how do I know that these reaction steps are elementary? What's the definition of an elementary reaction? So first of all, an elementary reaction is defined as a reaction that has a single transition state. Each of these elementary reactions in this mechanism has a single transition state. There's a second important property of each one of these elementary reactions that makes up my mechanism, and that is that they are microscopically reversible. What these two things mean in practice is that if I look at a free energy diagram, a reaction coordinate diagram for this reaction, I should have a series of hills and valleys that has two intermediates. I've got two intermediates in my mechanism, and three hills that would represent transition states. So if I draw an energy diagram for this, it needs to have three transition states to match the three steps in my reaction. The principle of microscopic reversibility is not so important for Chem 201 in this course. But what it means is, microscopic reversibility means if I ask you the mechanism for the reverse reaction, it has to involve exactly the same intermediates. That's the importance of microscopic reversibility. Okay, so criterion number one, elementary reactions. That's what a mechanism is. It's a series of elementary reactions. Criterion number two for a correctly drawn mechanism is the curved arrows. Those are secondary to the fact that I broke this down into a series of elementary reactions. So I've got curved arrows on each of these steps. Now, the problem is, how do we define what a curved arrow is supposed to mean? We may have drawn all the structures correctly, but how do we know that we drew the curved arrows correctly? And so let's go ahead and talk more about this idea of what do curved arrows mean in organic chemistry. So to help us understand what does an arrow mean, these curved arrows that we draw in organic reaction mechanisms, let me take what looks like a detour and stop and consider some distance-dependent equations for comparing things in chemistry. For comparing one transition state to another, for comparing one conformation to another, for comparing reactants to products in terms of their energies. So there's two different types of equations that are typically used, and I'm going to start off with one of the first types of equations that students are introduced to in general chemistry classes. And it has to do with how you factor out the energy of non-bonding interactions. So how do you estimate the energy when any two molecules or species are interacting without forming bonds? And you can break this down or decompose it into these mathematical terms. And don't be put off by the math for now. We'll talk about this in just a second. We're not going to use equations very much in this class. Okay, so here's a well-known equation that's used for estimating the energy of any two things interacting. It could be a substrate in the active site of a protein. It could be two substituents on a molecule when they're interacting. So there's three different terms, three different things we need to think about when any two molecules or any two species come together. I think you will recognize this first part of the equation, the first term, as a Coulombic potential. So I'll go ahead and just write here Coulomb. So what is it that's important about this? There's two different charges, and whenever two charges interact, the distance between them matters. The farther apart they are, the less of an interaction between two charges. You may or may not recognize this second term, but this is a van der Waals interaction, and commonly quantified with something called the Leonard-Jones 612 potential. There's two different distance dependence terms here. One of them leads to higher energies. When you push two things very, very close together, two molecules, two substituents, they start to repel each other. The energy gets higher. But when things start very far apart, this should be r to the 6. When things start very far apart, initially there's an attractive interaction. The energy gets lower. These are good equations for thinking about non-bonding interactions, for thinking about charges on the inside of a protein. If I think about some sort of a lysine side chain that has a positive charge and a substrate that has a negative charge, this is a good equation for thinking about that. Or if I want to think about the interaction of two methane molecules with each other, There's nothing about this that suggests a chemical reaction to me, but the fact is that methane forms a liquid. There must be some attractive interaction between methane molecules that doesn't make or break bonds, but that causes the attraction. And if you compress the methane too much, it suddenly gets very hard to compress. And that's this term taking over. So this is a great equation for thinking about non-bonding interactions. So what's the equation that organic chemists use to think about the interaction between different species? And I'll write here bonding energy. But it turns out that this equation, this set of equations that we're going to talk about, will also work for non-bonding interactions. So the way that organic chemists factor out these different aspects of what leads to higher or lower energy starts off, well, let me give you the classical definition first. If I go back and I ask organic chemists from 20 to 30 years ago about what it is that dominates the interaction between two molecules, two species, two functional groups, they would typically answer, oh, it's sterics or electronics. Sterics plus electronics. And I will urge you not to decompose interactions in this simplified way. This is oversimplified. And so let's simply erase this. This is a bad idea to decompose organic interactions into these two terms. If you really want to understand the differences between two transition states, between two reaction pathways, between two conformations, we need to do just like this equation on top and decompose those interactions into three different terms. So I'm going to start off by drawing something that should look familiar to you, and that's this Coulomb's equation again. Molecules, or even parts of molecules, have a charge associated with them. The second part of this equation, I'm going to be very vague about the form of this equation, but it's distance dependent. As I take two organic molecules and I push them together, or two methyl groups on a molecule and I push them together, that interaction will start to lead to a higher energy. And then finally, the last part of this equation, you'll just have to hold on for a second and put up with my math. And I'll explain what these terms mean in just a second, or what they should suggest to you. Okay, so here's what I see when I see this term here. When I see this term here, what I see is that it's a negative term. That suggests that it's an attractive force. It leads to an overall stabilization or lowering in energy. We want things like that when we're trying to judge something to be favorable. What I see here is I'm supposed to be summing over something related to electrophiles and nucleophiles. That's this symbolism here. And when I peek inside of this term, what I see are coefficients on atoms. If I sum over all the atoms in a nucleophile, times some coefficient on all the atoms in the electrophile, and then there's this beta term that suggests orbital overlap. And then in the denominator for this term, there's a difference in energies. The energy of an electrophile orbital and the energy of a nucleophile orbital. This is about molecular orbital interactions. And the structure of this term suggests that these are going to be favorable. So let me just summarize using simple terms here. What do these terms mean? When I look at a chemical reaction and I try to judge whether that reaction is good, what three things do I need to think about? I need to think about charges. That seems kind of obvious. We just discussed that. That's Coulomb's law, the Coulombic potential. I need to think about sterics. When any two things interact and bump really close to each other. The closer I get, the more it costs me. And then finally, there's this mysterious third term here that relates to the interaction of filled orbitals with unfilled orbitals. That third term is molecular orbital interactions. Every time you see two reagents reacting, two parts of a molecule interacting, you need to think about these three features. So we have to decide what we're going to use arrow pushing to represent. Let me start off by drawing out a reaction here, and we can try to think about how these different factors come into play. So let me go ahead and draw out some sort of a nucleophile. That's this lithium enolate that I've drawn right here. And I'll draw an electrophile. This is methyl iodide. There's a lot of different possible reactions that I could imagine here. So let's start off with a simple one. Let's think about this lithium-oxygen bond attacking this carbon atom. I think you can all see that the iodide is ready to act as a leaving group. So one possibility is that this lithium-oxygen bond attacks carbon, and in so doing it breaks the lithium-oxygen bond. As the oxygen gets closer and closer to this carbon, if this really is the mechanism, the lithium should get farther and farther away. I should be breaking the lithium-oxygen bond as we attack. That's what that arrow means. Another possible alternative would be to keep the lithium atom attached to the oxygen throughout the entire reaction mechanism, and instead have the lone pair on oxygen attack the carbon. This second possibility, the second arrow that starts with a lone pair, means that the oxygen-lithium bond does not break in this step. And then there's a third possibility that has nothing to do with the oxygen bonding to carbon. It has to do with this CC double bond attacking and forming a bond ultimately to this carbon atom at the end. So do I form an oxygen-carbon bond? Do I form a carbon-carbon bond? If I want to break this down into its different components and judge which of these three possibilities is correct, I have to resort to these three different terms here. If I were to use charge as the meaning of my arrows, and ultimately we need our arrows to mean one and only one thing. We can't make it so that sometimes our curved arrows mean charge, and then sometimes our curved arrows mean sterics, and then sometimes they mean this molecular orbital thing. Because if arrows can mean anything, then they don't mean anything. So let's decide, what should we have our arrows mean? If we look at the charges here, most of the negative charges on oxygen, I would predict that you would make an oxygen-carbon bond if I pay attention to charges. Most of the negative charge on this enolate is on the oxygen atom. If I pay attention to sterics, I definitely would not want to make a bond to carbon. That's much more sterically hindered than this oxygen-lithium bond or the oxygen. And finally, if I pay attention to molecular orbital interactions, that's the aspect of this equation that would correctly predict that it is this carbon-carbon bond-forming reaction on the bottom which is correct, as opposed to these incorrect predictions of the oxygen-lithium bond or the oxygen lone pair attacking. Ultimately, when you look at what will provide us with the best predictive power in organic chemistry, it's molecular orbital interactions. This is what our arrow pushing, our curved arrows, should be taken to represent. The interaction of filled orbitals with unfilled orbitals. And so we're going to spend the rest of the quarter thinking about this and learning how to use this equality between curved arrows and arrow pushing and the interaction of filled orbitals with unfilled orbitals. I'm going to read a little bit from a book that dates back to the mid-1970s. This is a book by Ian Fleming called Frontier Orbitals and Organic Chemical Reactions. And since then, there's been a new edition that has come out that's got much more information in it. But it's missing some of the art that really drove my generation of organic chemists. And there's a section in this book that discusses electrophilic aromatic substitution. And somewhere here in this discussion, I'll read to you this little section, and I'll point out to you what's important and what's important to organic chemists. So in this discussion by Fleming, he says, however, we ought to be clear that this is a superficial argument, which fortunately works. Curly arrows, when used with a molecular orbital description of bonding, work as well as they do simply because they illustrate the electron distribution in the frontier orbital. And for reaction kinetics, it is the frontier orbital that is most important. These are seismic words, and so let me extract from that what you need to take home from that, because it defines our course. What Fleming said was that curly arrows, or curved arrows, work when they are used to represent the interaction of frontier orbitals, of filled orbitals with unfilled orbitals. And if you really care about kinetics, then you need to focus on those frontier orbitals. And I can tell you that I am interested in kinetics. And if you are taking this course, then you are interested in kinetics too. If you are interested in which reactions are fast and which reactions are slow, if you're interested in which reactions are plausible and which reactions are implausible, if you're interested in which mechanisms are right and which mechanisms are not right, or which mechanisms are plausible and which mechanisms are implausible, then you need to focus on frontier orbitals. Therefore, that's why we are going to make a rule out of this. That's what our curly arrows will represent. And so let's set down this central canon of mechanistic arrow pushing. We'll define this so that now when any two people in this class draw out a curved arrow mechanism, we're all drawing the same thing. So the test that you'll apply every time to check whether your mechanisms are correct with the correct arrows is, have you used curved arrows to depict the interaction of filled molecular orbitals with unfilled orbitals, and in particular with filled frontier orbitals and unfilled frontier orbitals? So let me give you an example that just to suggest that you've probably been doing this whether you recognize it or not. This isn't something new. In fact, you've probably been doing this from your first days drawing out reaction mechanisms as a sophomore in an organic chemistry course. Here's an extended enolate that you could get by deprotonating an aldehyde. And if I make this interact with some sort of an electrophile, in this case iodoethane, the mechanism I would tend to draw would involve carbon-carbon bond formation between this carbon right here that has a dot and this reactant ethyl iodide, the electrophile. These correctly drawn arrows represent the interaction of filled orbitals with unfilled orbitals. When I draw this out, I can think about the structure of an enolate as being the result of the interaction of this non-bonding orbital on oxygen. We have a label that we give it. It's this italics N, which means basically lone pair, non-bonding orbital, centered on oxygen. And it's donating into pi star. So there's an unfilled orbital here that's called a pi star orbital between two carbons. Likewise, I have a filled orbital here, and that's this pi orbital between two carbon atoms that's donating into a sigma star orbital between a carbon and an iodine. So even without these fancy looking labels here, this mechanism is correct. And I know that it's at least plausible because I've drawn out the interaction of a filled orbital with an unfilled orbital and a filled orbital with an unfilled orbital. And so this is the intent of arrow pushing. Okay, so let me just remind you of what our goal is for this class. Our goal for this class is to break down reactions and draw arrow pushing mechanisms. And every arrow pushing mechanism should be composed of a series of elementary reactions. That's reactions that have a single transition state. That's how I know that it's elementary, not multiple transition states. And then secondarily, I add curved arrows to that series of elementary reactions. And each one of those curved arrows represents the interaction of some sort of a filled orbital with an unfilled orbital. And that's the goal for this class. So when we come back for our next sort of topic, I'll give you 7 rules for mechanistic arrow pushing that allow you to make sure that you are doing this correctly.